Hello everyone. In lab you were looking at moment of inertia and how it relates to torque and angular acceleration. Now the linear equivalent of this is Newton's second law, which is net force equals mass times acceleration. The size of a push given to an object is directly proportional to its acceleration, and the more mass something has, the less acceleration it will have for a given force. The angular equivalent of this is slightly different. It says the net torque is not equal to mass times angular acceleration, but rather moment of inertia, or I, times angular acceleration. Moment of inertia is actually an interesting thing. It depends on mass, which doesn't surprise us. The more mass something has, the harder it is to accelerate, so it should depend on mass, but it also depends on shape. And primarily the shape is the distribution of mass. Okay? And here's what I mean. You guys are familiar with this already. When you were little and you used to twist the chains up on the swing and then spin in a circle, the chain was applying a torque to untwist you. It wanted to be untwisted, and that torque caused you to accelerate. Now what you realized was if you pull your legs in, you spin in circles faster than if you kick your legs out. And the reason is you're changing the distribution of the mass, which is to say you're changing the moment of inertia or resistance to angular acceleration. So if you have your feet kicked out, then you're putting a bunch of mass out here on the outside. Okay? If this is a bunch of mass out here, then this all has to accelerate through a big distance, and it's hard to get mass to accelerate. But when you pull your legs in, then most of the mass is concentrated in here, and there's not very much mass out here. Since there's less mass out here, it's easier to accelerate it. Okay, so when I say I depends on mass and it depends on the shape or the distribution of the object, what we have is the formula that I is equal to m times r squared. But this is only true if the mass is concentrated at a point. So not a disk, not a cylinder, not a rod, but all the mass is concentrated a certain distance r from here. So it could be a thin hoop with all the mass on the outside. So if we have something like this, the axis of rotation here, then this actually has a moment of inertia equal to mr squared. But if we have a solid disk, and imagine that this solid disk has the same mass as that thin hoop we had just a second ago, since some of that mass is actually brought in towards the center, it's easier to accelerate it because its acceleration is less, I guess. It takes less force to accelerate it because it has less linear acceleration in here. So what we see is this thing, a solid disk, actually has a moment of inertia equal to 1/2 mr squared. So the distance of the mass from the axis of rotation gives us an idea of what should happen to our moment of inertia. So this is the maximum moment of inertia. If all the mass is r units away from the axis of rotation, everything else is a little bit less than that, because if the mass is brought in closer to the center, then some of the mass has a smaller radius, and so we have to account for that. There is a list of these in your book. There are a couple I want you to be familiar with. You should know the thin hoop or the point mass. So this is a point mass, okay, r units from the center. This is a disk, radius r, mass m. If you have a sphere, and the sphere is hollow, okay, so there's no mass in here, it's all distributed around the outside, then I is equal to 2/3 mr squared, and that is for an axis of rotation through the center of the sphere. If you have a solid sphere, remember that roller coaster lab we did where we had a solid steel marble? If you have a solid sphere, then I is equal to 2/5 mr squared. Now why is this one 2/5 mr squared smaller than that one? Since all the mass is concentrated on the outside here, there's none in the center, all of this mass has to be accelerated through a big distance. However, with a solid sphere, that same amount of mass gets distributed to a bigger volume. It covers more volume. There's some on the inside now with less radius, so we have a less moment of inertia. Then there's ones for rods. If you take a rod, long skinny beam, and you spin it through its end, then I is equal to 1/3 mr squared, or I guess a lot of times you'll see L for the length of the rod. If instead of spinning it through the end, you spin it through the center, then I is equal to 1/12 ml squared. And the reason for that, again, more mass is closer to the center. Here you've got this mass close to the center and the rest of it's kind of far out. Now this mass is all close to the center and none of it is as far out as it used to be. So 1/12 ml squared. Like I said, there is a table in the book on different moments of inertia for different shapes. Now, I do want to look at the units of moment of inertia. We have torque divided by alpha, angular acceleration, is moment of inertia. Well, remember, torque has got units of Newton times meters, and angular acceleration has units of radians per second squared. Now, I'm going to do a little bit of simplification. Remember, a Newton meter is a kilogram meter per second squared. I have that multiplied by meters, and all of that is divided by radians per second squared. Now remember, a radian is just a placeholder. It's a dimensionless unit because it's calculated distance to distance. It's a ratio of arc length to radius. So I have meter times meter, which gets me a kilogram meter squared per second squared. And now I can invert and multiply my second squared per radian. Second squared cancels my second squared. My radian is just a placeholder I don't need anymore. So a kilogram meter squared. This is the unit of moment of inertia, kilogram meter squared. And if you think about that, that matches our formula exactly, where we said I is some k, depends on the shape, times m r squared. So different shapes have different k values, but those are just numbers. We still have a mass times a distance squared. So moment of inertia is that rotational equivalent of mass, and it tells us how much torque is required to accelerate a given object with a given angular acceleration.